Hello there, and welcome to another quick maths tutorial. Today I'll be doing it on Prim's algorithm, which is in first year, decision 1 of A-level further mathematics. So this is like Kruskal's, as we'll see. It's how you get a minimum spanning tree by applying this algorithm to a graph. So yes, just have a first look at what it does. So it finds a minimum spanning tree for a graph like Kruskal's does, as I've just said. It is often quicker to use Prim's, actually it's a faster algorithm, we'll see why. However, because you don't need to consider cycles like you do in Kruskal's, where you have to think about adding each edge and you think, will this cause a cycle? And Prim's you don't have to, which, less to think about. As Prim's deals with vertices, whereas Kruskal's deals with edges. So it can be, you can actually do Prims to the graph itself, which you'll be doing it on. So from the graph like we do with Kruskal's, or you can do it from a distance matrix. So all together, which we'll look at in a minute, which is basically like a table with all the weights of all the arcs in it. So we don't actually have to look at the graph or have the graph with us to do Prims. So first, let's look at the graph method. I've got a graph here. By the way, the matrix method will be the same graph, but I will have turned it into a table first. So yes, straight into it. So to do Prims, we have to have a starting node. It doesn't matter which one, because every node will eventually be included, but we do have to start somewhere. So I've chosen A to start. Then we choose the arc from A with the smallest weight. So as you can see, A has got 3 arcs, and the smallest is 7 from A to C. So there you go. That is the smallest arc. So what we say now is that A and C are discovered nodes, because we've been to them. That sorry. In our minimum spanning tree, so far as we're building it, A and C are already included, so we've got discovered. Now to build the minimum spanning tree, we don't want to go back. We want to just include new nodes, so undiscovered nodes, which would be B, E, F, and D so far now. We don't want to go back to A and C, so any arcs going to A or C, we don't want, basically. Although we can go from A and C to other undiscovered nodes. So the direction on any of these arcs doesn't matter, but basically any arc from A to C we can't use. So now we're only going to consider arcs from discovered nodes to undiscovered nodes to prevent cycles, essentially. Though we don't have to consider them. So my face camera thing might get in the way for the text, but essentially we can now choose from AB, AD, CE, CF, because those are all from, basically we want to go from discovered ones, so A and C, to undiscovered ones. So we can only go from A or C, and that so happens to be to B, to D, to E, or to F. And those are the 4 arcs which we could do so. The smallest one is A to D, if we could just find that there, A to D, because that is of weight 10. Then in this order, so I'll choose them. We want to pick D to B, which is 9, as that adds B back into it. Then we choose C to F, that's 14. That includes F in it, and then finally C to E, because E is the last one we need to add in. We need to get to E somehow, and we need to go from any discovered one, which is all the others, and the shortest one to do that is from C to E, because that's 19. See, that's the smallest number going into E. And that is our minimum spanning tree done. Notice how we've included every single node now. There is a way to get from every single node. Alright, now the table. So again, this entire graph can be represented by this what's called a distance matrix. Again, my face thing is in the way. I'll read the text behind that anyway. If you were to look at any cell or element in this table, it's in a row and it's in a column, and essentially how you deduce what this number, or sometimes not number, represents is that is the weight of the arc going from this vertex in the row to the vertex in the column. So I can see I've circled the red one, that is D to E, but also E to D, because this is an undirected graph that is the same arc, because it goes both ways. It allows you to go back and forth from D to E in it. So it should be perfect symmetrical in this leading diagonal if you think of it like a matrix here. And as you see, that represents the arc on the graph E to D or D to E, which is 22. And sometimes when I have a slash in it, that just means there is no direct arc connecting these two together. So as you can see across the leading diagonal, it's all slashes, A to A, B to B, because you can't do that. There is no arc connecting itself. Yeah, it's the same thing. That's why I've got the arrow connecting there. So let's actually apply it to this table. So first off, I prefer applying a table. We have to pick a starting node, and we delete its entire row like that. This ensures we'll never go back to it again, because these are all arcs connecting it. We don't really want those anymore, because these are all ways to go to A. Then we pick the smaller numbers as a column. So these are all arcs from A. As you can see, we've got 13, 7, 10, and then slash slash, because we can't go to E or F. The smallest one is A to C, which is 7. So we circle that. And then we delete that row, because we don't want to go back to C now, because C is now a discovered node. So we delete C's row. Then we pick the smallest arc, which is in the original column, so A's column, or the newly deleted nodes column. So that is C's column as well, so A or C. And this is essentially the same as arcs going from A or C. However, again, we don't want to go back to A or C, which hence why we've deleted A and C's row, so we can't do that. So we only pick from the rest of the remaining A column and the remaining C column. This ensures no cycles happens. So you see I picked A to D because that's the smallest one, that is 10, circled that. And basically we repeat this entire thing until we've deleted every single row. So if you can guess what we're going to do next, we've just picked an arc, so we're going to delete its row, we're going to delete D's row, and then we're going to consider arcs, the smallest arc in A, C or D, which is D to B, you see there. So circle that, and that links us to B. So we're going to delete B's row. There we are. And A, B, C or D, we can now pick from. The smallest one in there should be 19. Oh, sorry, 14. C to F, 14 is the smallest. There it is. And we delete F's row. And lastly, we've just got E's row to pick from. We can pick from any of the columns A, B, C, D or F, all going to E. And we pick 19 because that's the shortest way to get to E. And we delete E's row, and we're done. That is the algorithm done. We've got our minimum spanning tree, and you can basically, if you remember the order, you just write down in order of the arcs you've chosen. So we've chosen A to C, A to D, D to B, C to F, and then C to E, with the arcs chosen in order. And that is our minimum spanning tree. You can add up all those numbers for the weight if you'd like. So this is an alternative to Kruskals. I hope you enjoyed this video, and I will be doing more algorithm and graph videos in the future. So that's it for now. Thanks for watching.